Hey, how's it going? It's time for us to do a new video, and today we're going to talk about friction force. First of all, I kept this going on Saturday, and my daughter, my 6-year-old, Jordan Grace, I love you. Jaden, I love you as well. She drew this beautiful little picture of a horse. I don't know if you can see it, but it's on my door now. So yeah, I loved it. She's so good. Very talented like her mother. Alrighty guys, let's go ahead and get right into it. So, friction force, an intro to friction force. If you don't know what friction is like what you get when you rub two surfaces together. Like if you have a shoe on and you're running on carpet, you'll have a lot of friction there. You'll be able to run, make sharp turns and all that. But if you're on tile and you're wearing socks, you're going to be sliding all over the place. It's because, the friction force, or the coefficient of friction between socks and tile is very small. Alright, here we go. Let's go ahead and get started. Oh my gosh. Alright, here we go. So, friction force. Our first official notes. You will write it like this. Capital F, lowercase f, friction force. Friction force always opposes motion, and it is always perpendicular to normal force, just Fn. The symbol for the coefficient of friction, that's the how much friction there is between two surfaces, is this symbol right here. That is the word, or the letter mu. I don't know if that's how you spell mu, but that's how you say it, mu. Alright, if an object is sliding on a surface, you will use mu k. K being for kinetic. And what does kinetic mean? Moving. We'll talk about that later on when we go to kinetic energy and potential energy. And you use this when an object is sliding on a surface. You will use mu s for static friction. That's when the object is not sliding on the surface. So let me give you an example really quickly. Let's say a car, you're driving a car, right? Here it is, I'll just do it with my hands. You're driving a car. Here's the car. Here's the car's tires. Here's the road. When you are driving the car at 60 miles an hour, do you think that that's kinetic friction or static friction? Let's see. Well, here's the car. Here it goes. Wheels are going on the road. That's the wheels turning. Is that kinetic friction or static friction? Well, are these wheels sliding on the surface? Are they sliding on the surface like this? No, they're not. They're just turning on it. So that is static friction. Even though the car is moving, the wheels are not sliding on the surface, so it is static friction. What if all of a sudden you hit the brakes really hard and you do this? What's that? Good. That is kinetic. Why is it kinetic? Because it's sliding on the surface. Super good. Stops. Alright, so here you go. Here's another note you may want to make. Kinetic friction will always be less than static friction, but greater than 0. Here's an example. Here's a gentleman. He's trying to push this box. There's a box. He's pushing the box. The box has not started to move yet. Here's some little motion lines. By the way, I don't know, my tongue is hurting, so I feel like I'm going like my tongue is feels like it's super big right now. I don't know why. Alright, so if I'm talking weirder than usual, that's what it is. Alright, so here's the guy. He's pushing this box. I don't care about how much it weighs right now, that's not important. Let's say his symbol for the coefficient of friction between this box and the surface of the floor is 0.90. Let's just say it's 0.90. Once this box is moving, is that still mu s or is that mu k now? Mu k, why? Because that box is now sliding on this surface. Here's some motion lines that show that the box is moving. Will the kinetic the coefficient for friction, will it have gone up above 90 or will it drop lower than 90? Kinetic friction will always be less than static friction. Let's just go ahead and give it a 50. Oh, it looks like a 58. Let's give it a 50. So let's see. Before the guy starts pushing the box, he's like, alright, ready, here, I'm about to move this box. 1, 2, 3. He's pushing. The coefficient of friction is 0.90. Once he finally breaks that barrier of 0.90, the coefficient now drops down to 0.50. So, is it easier or harder to move this box now? Is it okay? If you were going to move that box, should you move it a little bit at a time? Should you go, take a break, take a break? Should you do that, or should you just go and just push it all at once? What do you think? Yes, you should push it all at once to get it out of the way, because the coefficient of kinetic friction will be less. It'll take less force for you to get that box off once you have started it to move. Newton's first law: an object in motion will tend to remain in motion unless acted upon by an outside force. So once you've got it going, don't stop. Please don't stop the music. Next slide. Special cases for friction. Here we go. Let's see. Write this down, please. Well, I don't know if you know this or not, but let's see. If you don't know it, here's some equations. Here's your first equation when you're dealing with friction. Equation number 1. Friction force is equal to, what letter was that? How do you say that thing? Mu, could be K, could be S, whichever one they give you, times your normal force. That's equation 1. Equation 2 is this one. Newton's second law, what was it? Newton's second law. Force is equal, it's FEMA. Force is equal to mass times acceleration. There it is. It's not really FEMA, but that's how we say it in class. Alright, so you have these two equations. Alrighty? I don't know if anybody's ever broken these down to you, but I will go ahead and do these for you really quickly. Let's talk about equation number 2. Let me just draw this for you. Here's a free body diagram. Let's say it says mass times gravity. That says normal force. Let's say it's on a surface. Here's your force that is applied. It is not FAP. I know. Next, this is friction force. Let's say we're trying to move this object to the right. Friction force will be opposing the motion. So the motion is trying to go to the right. So the friction force will be pulling it to the left. Dang, I don't know if my hands are going the right way when I'm doing this. Well, it's alright. Alright. This force equals mass times acceleration. You can break this down. You can rewrite it like this. Net force is equal to mass times acceleration. Right now, when we're talking about friction force, what direction are we going in? Are we going with the Y direction, up and down? Or are we going in the X direction, side to side? Yes, we are going in the X direction, side to side. So do I really care about the up and down right now? I don't. Good, I'm glad you don't either. So we can go ahead and rewrite this as your net force in what direction? X is equal to your mass times your acceleration in the X direction. Alright, now let's go ahead and go to our free body diagram. Let's just scratch out everybody who's not X direction. Is the Fn in the X direction? Nah, I'm not worried about it right now. How about the mg? I'm not worried about it either. Who am I worried about? Friction force and force applied. They are in the X direction. So watch what we're going to do here. The net force of something, is what you have left over. After everything is said and done, what do you have left? Like your net pay on your check? It's way smaller than your gross. That's after your taxes and all that stuff. So here we go, let's see. So how many forces are there in the X direction? Well, there's force applied and there's also friction force. So how many are there? 2. Good job. So I'm going to draw 2 little lines. I'm going to put force applied. What's the other line going to be for? Friction force. Good. And I'm leaving the back the same. I'm leaving the mass times your acceleration in the X direction. Yes? Okay. Now, what does force applied and friction force? Let's see. There should be some kind of sign here. Are we adding them or subtracting them? Let's see. If you go back to vectors, vectors going in the opposite direction, what will they do? Will they add or will they subtract? They will subtract. Very good. So you have your force applied and you've got your friction force. Your friction force is going to be taken away from your force applied. So we will use something like this. But here's what you really need to remember. That guy. So the net force in the x direction, well, there are two x forces. We listed both of the x forces, and since the friction force was going in the opposite way as the force applied, we are going to write subtract. Okay, so the bell just rang, so there'll be tons of students coming to my room right now, but hopefully we can finish this video. Okay, ready? So we got this. There's not really anything to do to this guy. We just leave him alone. Okay, now watch this. Watch this. Watch this. Watch this. Special cases. If, when you're doing a friction force problem, you see this little phrase. If you see this, watch, check it out. If you see that the object is being pulled at a... Hold on, somebody. Okay, go ahead. Just come on and clap. If you see that the object is being pulled at a constant speed, that's a huge, huge, huge tip. Huge tip. Constant speed. Because that means that your acceleration is going to be 0, and that means that we can use this equation. Oh, sorry. Yeah, we can use this equation right here, the F net equals mass times acceleration. That means that your F net equals mass times acceleration, which is now 0, really just goes away. This whole side just goes away. So you are left with force applied. I'm sorry, I just broke down the F net. Subtract your friction force equals to 0. And if we just add friction force to both sides, we end up getting this. Force applied is equal to friction force. So we have that. So this is the big idea. That's the big. When you see constant speed, that means force applied is equal to your friction force. Force applied is equal to friction force. When is it equal to friction force? When it says constant speed. If it doesn't say constant speed, then you can't do it. Alright. So, if force applied is equal to friction force, then that means we can... Close the door. Come in and go out. See ya. Then that means we can do this. See this equation right here? Friction force is equal to mu k or s times net normal force. Because we said force applied is equal to friction force, we can swap the friction force out and put force applied if we needed to. If we had to do this, if they only gave us force applied, we can just pop it right in here and get our answers. So that's a special case. What's the special case? When it says constant speed, that means force applied will be equal to your friction force. When it says constant speed, that's huge. It's going to help us do our work. Here you go. Here's a table. If you're doing friction problems, you may see a table like this on your test. It'll be in a box. Sorry, this is kind of ugly. I didn't think I was going to use it, but I'm using it. You'll see a box with stuff. For example, it says rubber on concrete. The coefficient of static friction is 0.8. Your coefficient for kinetic friction is 0.65, and rubber on wet concrete, you know, that's your mu k values to use if you need to. Alright, sorry, so here we go. Let's get back to finishing this up. Okay, last time we left with this table. You'll get this table. Be sure you know how to get your coefficients of friction, whether it's static or kinetic, and you've got to read the problem to see which one you need. Alright, let's go. Next slide. You push a 25 kilogram wooden box across a wooden floor at a constant speed of 1 meter per second. How much force do you exert on the box? Well, first of all, let's pull this very important word out. Constant speed. What does that mean? Constant speed means that your acceleration will be 0, but more importantly, it means that your friction force will be equal to... get used to writing it like this. It means that your force applied will be equal to your friction force. That's what that means. Because it said constant speed, we can now say this. Force applied is equal to constant force. Alright, let's go ahead and draw a free body diagram really quickly about this thing we got going on. There's the wooden box. First arrow we always draw is the arrow going downward. That's mg, that's mass times gravity. What's the mass of this object? 25? Well, let's just go ahead and figure out what its mass times gravity is. The little gravity. You are going to have 25 times 9.8, and you get 245 newtons. It's on a wooden floor, so what does that mean? That means that normal force is going to be the same thing, because the box is not falling through the floor. The floor is not pushing the box up, and there's a force. Which way is the force going? We don't know, but let's just assume it's going to go to the right. That's going to be your force applied. We don't know. Well, there's something important you need to pick up on, and it's going to be this. You see how it says a wooden box sliding across a wooden floor? Well, what kind of surface is that? That's a wood on wood. Well, let's go back to the table that they gave us. Like, they're not going to say, refer to your table on your coefficients of friction. Well, let's see, your coefficients of friction. Do we need rubber on concrete? No. Rubber on wet concrete? No. Yes, here it is, wood on wood. Let's go. Do we want the mu s or do we want the mu k? Let's see, let's go back and read the problem. The wooden box, you're pushing the wooden box across the wooden floor. So is the box staying still? Or is it probably sliding? Good, it's sliding. So we're going to use that, 0.20. So we know that the coefficient of kinetic friction is 0.20. We got that? Now let's write both of our equations. The first equation is friction force is equal to coefficient of friction, in this case it's mu k, times your normal force. Next one is going to be your force is equal to mass times acceleration, but we know that that is now net force in the x direction equaling mass times acceleration in the x direction. Okay. So, let's see, what are we going to do here? Well, we have mu k. We want to use that. Can we use it in this first equation anywhere? No, we can't. We cannot use it there. Can we use it in that second equation? Yes, we can. So we're going to use this second equation. So we have friction force is equal to mu k times normal force. Sorry. Alright, your friction force, do we know what it is? We don't know. Do you know what your mu k is? Yes, we do. 0.20. Do you know what your normal force is? Or for those of you who don't know, your normal force is always perpendicular to the surface. And since this box is sitting on a surface, this Fn is going straight upwards, and it's going to be 245 newtons. Oh, I forgot that. So we have that. And then we have friction force right here. But does it want to know friction force? How much force do you exert on the box, or does it want the force applied? Well, it wants force applied. So, because it said constant speed, we can erase friction force and replace with force applied. So, we go ahead and do 0.20 times 245 times 245. And we end up getting 49. 49 newtons. There we go. You're done with the first one. Wasn't too hard, hopefully. Second one. If the force you exert is doubled, yikes. If the force you exert is doubled, what's the resulting acceleration on the box? Well, let's see. Let's go ahead and write down our two equations. It is friction force is equal to mu k times your normal force. Your other one is F net x direction equals mass times acceleration, x direction. Which one of these has acceleration? Because we're trying to find acceleration. Is acceleration in this one? I don't see it either. Is acceleration in this one? Yes, it is. So we're going to use that second one. So we have F net equals mass times acceleration in the x direction. And we're going to get the information from the last problem, because if the force was doubled, well, let's use the stuff from the last problem. Let's see what we got here. We've got, what's the mass? The mass of this object is 25 kilograms. So we're going to write 25 kilograms, or 25. We don't know acceleration, so we're going to leave it as AX. And we have F net Let's see. And we're gonna, let me just draw the free body diagram here. Here was your box. That was your mg. Your mg was 245 newtons. Your normal force was also 245 newtons. Your force applied was 49 newtons, but we're going to times that by 2 because it says doubled. And your friction force, because it was constant, is the same as 49, because your force applied is equal to your friction force when this object was moving at a constant speed. So we do 49 times 2. 49 times 2. Enter. You get a 98. So your force applied is now 98. Does that mean he changes to 98? No, it didn't say double him as well. It doesn't say he's still moving at a constant speed. It says, let's find the acceleration when you double the force only. So, our F net, what direction do we care about? Do we care about the Y direction? Or do we care about the X direction? We care about the X direction, so I'm ignoring those, but I'm concerned about these. So you break it up. You've got your force applied. Subtract your friction force because they're going in opposite directions. Your force applied is 98. Your friction force is 49. And I'm keeping this other side of the equation the exact same as it was. 98 subtract 49. Type in the calculator. You got 49 is equal to 0.25. Acceleration in the X direction. So how do you solve for this? You're going to need to divide this 0.25 to the 49. So let me just go ahead and rewrite right here. 45 equals to 0.25. If you don't know the algebra, I'm going to show it to you right here. 0.25. That will reduce to 1, so we ignore it. It cancels out, but it doesn't really cancel out. It turns into a 1. And you got 49 divided by 0.25. That gives you 196. Whoa. That sounds weird. Why does that sound weird? Acceleration of the box. Here, acceleration of the box. It shouldn't be that big. Why is it that big? What did we do wrong? I know what we did wrong. Oh my gosh, I'm an idiot. You see all these 0.25s that we did? Those are all wrong. They shouldn't be 0.25s. I wrote the 0.25s because I saw this 0.20 in it. I don't know. I'm so stupid. I'm sorry. So there should be no decimal there. This decimal should go away. No decimal. No decimal. No decimal. 49 divided by 25. Enter. There it is. There we go. 1.96 meters per second squared because it is acceleration in the X direction. Alright. So here you go. You learned a little thing about this problem, and it's okay if you make a mistake sometimes, as long because the answer I got was this. It would have been 196 meters per second squared. I was like, that does not sound reasonable, which made me check my work. So be sure you guys use your reasoning as well in your next problem. Problem number 2. A boy exerts a 36 Newton horizontal force as he pulls a 52 Newton sled across a cement sidewalk at a constant speed. Oh, keyword right there. What was it? Constant speed. What does that mean? It means that your force applied will be equal to your friction force. And it wants to know the coefficient of kinetic friction. So we are looking for mu k. Alright, let's draw a free body diagram. There's the sled. Oh wait, are we talking about the boy or talking about the sled? What's the free body diagram going to be about? Well, the boy is exerting a force on the sled that he's pulling. So this will be representing the sled. And his mass times gravity down is going to be careful on this. You see how it says 52 newtons for the sled? You will leave that as 52 newtons. You're not going to multiply by 9.8 because it's already in newtons. So since it's on the floor, what does that mean about the normal force? Is there a normal force? Yes, there is, because he is on the sidewalk. Normal force, there it is. It's got to be the same because it's not going through the sidewalk and it's not floating in the air. Your force applied. Where's your force applied? Well, the boy is exerting a force of 36 newtons horizontally. So we'll go to the right. Oh. Force applied is equal to 36 newtons. And we know that because it's moving at a constant speed, the friction force which opposes motion will also be 36 newtons. Okay. So, some students say, so the sled's not even moving. But is the sled moving? What do you think? If all of these forces are equal, if the net force of all this is zero, Newton's first law, then the object will continue to stay in the state that it's in. So if this sled is moving and all these guys cancel each other out, the sled will continue to move at the exact same speed it was moving in. If the sled was not moving and all these forces cancel out, then the sled will continue not to move at the exact same speed it wasn't moving in. It just means when all the forces are equal, when they all cancel out, it'll continue to do what it needs to do. Alright, next thing. It wants to know the coefficient of friction, so we have our two equations. The first one is friction force is equal to mu k, or S, times normal force. The other one is F net. X is equal to mass times acceleration in the X. Which one of these has the coefficient of friction in it? Which one has the mu k in it? The first one? No, perfect. This one does. So we're going to go friction force equal to mu k times normal force. What was your friction force? Well, because it's at constant speed, we know that it's equal to the force applied. So we can go ahead and write a 36 right there. Your mu k is going to be, we don't know yet. And your Fn was 52. So you're good. Now solve it for mu k by dividing each side by 52. That reduces to 1. It does not cancel out. And then you got 36 divided by 52. Enter. And you end up getting 0.69. So I'll write it over here. So your mu k is equal to 0.69, and there are no units on it. It's just that. So if you got that, you're good. Last one. And we're done. Yes. Suppose a sled, the same one from the last problem, now runs on some packed snow. The coefficient of friction is 0.12. Uh-oh. That's mu k, and that's going to be 0.12. If a person weighs 650 newtons and sits down on the sled, what force is needed to pull the sled across the snow at a constant speed? Constant speed. That is going to mean what? That your friction force is going to be... Oh, I keep writing it backwards. It's going to mean that your force applied is going to be equal to your friction force. That's what constant speed means. So, here's your free body diagram. There's your sled. How much did it weigh in the beginning? 52 newtons. Sorry, it was right here. Let me just show it to you. It weighed 52 newtons. So the sled is weighing 52 newtons, but now a person weighing 52 newtons sits down on the sled. What are you going to do with that 650? You're going to add it to the 52. So you got 650 plus 52. That's going to equal 702 newtons. That's the force of gravity on it. This sled is on snow, so there is a normal force. That normal force is 702 as well. And we don't know what the friction force is, but we know that there will be friction, and then we don't know what the force applied is. We're not too sure on that. So, let's see what we got to do. We've got to find the force. What force is needed to pull the sled? First equation is friction force is equal to mu k or mu s times Fn. The other equation is F net, usually in the x direction, is equal to mass times acceleration in the x direction. Well, which one of these has this mu k that we can use? The F net or the friction force? Good, friction force does. That's the one we're going to use then. So we're going to have friction force equal to 0.12 times your normal force. Where's your normal force? Oh, here it is. 702. So we do 0.12 times 702, and we get 84.24. Oh, but this answer was for friction force. If only we knew what the force applied was. If only we knew that. Oh, well, it does say constant speed, and when it says constant speed, that means that your force applied will be equal to your friction force. So we can just go ahead and do this to it. Force applied is equal to 84.24 newtons. Why could we just make this little switch at the end? Because it said constant speed. That's the big deal when it comes to friction. Look for that. That will make your life easier. Thank you very much for your time, and be sure you check out the next one. Have a wonderful day, and we'll see you later.